quantifiers. Yeah. So we want to prove that f is uniformly continuous. So for all epsilon, we must find some delta so that for all x and y, if the distance between x and y is less than delta, then the distance between the images is less than epsilon. So just fix any positive epsilon, and I will introduce this subset k. So in the product x times x, I look at all points whose images are sent at distance more than epsilon. And this k is closed because f is continuous and the distance function is continuous. And since x times x is compact, this k is compact. And I will use compactness of this set k. What is it lagging like this? The extreme value theorem gives me some point p in k, so that for all q in k, the distance between the first component q1 and the second component q2, so k is in the product x times x, so q1 is the first component and q2 is the second component, is more than the distance between p1 and p2. And then the delta I'm looking for in this formula will be the distance between p1 and p2. And I say that now for any, yes, I forgot to fix that mistake. For any x and x prime in x, there should be x and y to be consistent with my notation above. I need to prove that if the distance between x and y, so this is a y, and is less than this delta that I've chosen, then the distance between f of x and f of y is completely messed up. Y and x prime are the same thing. Sorry about that. But the contrapose of this implication is exactly the property that I had for P here. So this is the end of this proof. So this is the proof I want to explain to my computer. Okay, I want to prove a uniform continuity of continuous function on compact metric spaces using this proof. So now I can start with maybe trying to copy paste this proof in a computer program. So let's try that. And why not? Where is my here? Sorry. Where the program disappeared. But... So let's try to do that. So this is the computer now has a statement of this rule. Ah, bien. Yeah. That's much better. Okay, so I've got the statement of the theorem here. So I've got metric space X and metric space Y. Assume that X is a compact space. F, I've got an assumption that is called HF, that it says that F is continuous, and the goal is to prove that F is uniformly continuous. And of course, there is an error message saying there are unsolved goals here because I haven't proved anything yet. So I just try to paste the proof, and this is a bit disappointing. Now there is red all over the screen, not only at the end of the proof, because we are not yet at a point where the computer can understand something like this. I mean, there are people who think that they could manage that in the future, but for now, this doesn't work. So I will simply comment all this and try to write a proof, but following this outline, but without having the computer actually reading what I've written. So the first thing is I want to say that the goal is indeed this thing. So I know that how to tell the computer to use the definition of uniform continuity. So I'm typing, you see on the left-hand side, I'm typing commands, and this command is rewrite using the lemma metric.uniform continuous if and only if. And now the goal has changed on the right-hand side. This is the computer answering my commands. So you see all the things we have as assumptions. So X is equipped with a metric space structure, and Y is also a metric space. I've got my function, my assumption, and after this funny symbol, which is like sideway t is the current goal. So this is the goal that I expected. And now I need to fix some positive epsilon. So there is a command doing that, says introduce some epsilon and an assumption saying that epsilon is positive. And the computer is happy to do that for me. And now epsilon is fixed here. And I've got this assumption that I named epsilon post, saying that epsilon is positive. And the next line was to introduce k. So I can almost copy that line actually, but not completely with the same syntax, but almost. So the distance between f and p1 will be written like this. So the parentheses are a bit weird, but otherwise you can read this. I mean, the computer scientists think that you don't need parentheses around arguments of a function. So f space p dot 1 is a good way to say f of p1. But then if you don't put any parentheses at all, then the computer is confused because it thinks that you want to apply the distance function to f and then p1, and then there are training arguments you don't know what to do. So we need the couple of parentheses. Okay, now let's start the proof. So the first claim was that k is closed. So I'm just claiming this is true, and now I'm asking. So I've claimed something. And I named it k closed. This is the name of my claim, and my claim is that k is closed. And now I've got two goals on the right-hand side. The first goal is to prove the claim I just made, and then the second goal is what I was doing before, but with an extra assumption that is my claim that I just proved. And now, how could I prove that? Maybe I will ask for suggestion from the computer, because I don't know the proof. Was k is closed because f and distance are continuous. So let me see what the computer suggests to do. And okay, there are a bunch of suggestions, and that one looks promising. Is closed L less or equal? So let's refine this idea. And now I need to prove a lot of things. Now I've got three goals. I need to prove that the constant function with value epsilon is continuous, and I need to prove that the right-hand side, p goes to distance between f and p1, and f and p2 is continuous. So this is a boring continuity proof. So let's ask the computer to do the continuity, all the two continuity proofs that we have to do. So this is okay. And now I've got, the command I use is simply do a boring continuity proof form using the assumption. And then we can ask the computer what it did, but we'll do that later. Or maybe we can do that right now.
But the computer does this, or you assume that it's true?
No, it found the proof, okay. And we can ask what was the proof that was found. And for instance, for the first continuity proof, it says that what it did was actually saying this is exactly the lemma called continuous const. So this is a continuity of the constant function with value epsilon. And if we look at what it did for the second one, so maybe I will say, okay, this the second continuity proof, the continuity proof that it found was this hf, which is my continuity assumption for f, dot comp, so composed with continuous first, which is a lemma saying that the first projection on the product is continuous, and then continuity of distance is used there, and what is this? And again, continuity of f composed with continuity of second projection. So if we want, we can tell the computer we want to see details about the proof it found, and if it's unclear what is this proof that it has found, I can just put my mouse over this continuous first here, and I see this little pop-up telling me that this continuous first lemma says that for any topological space alpha and beta, prod.first, which is first projection in a product, is continuous, and so we can have access to everything that the computer did for us. So it should go a bit faster, but you get the idea. Now I want to say that k is compact, and again, the computer should be able to do that for me, just asking for suggestions. And there is a suggestion that is simply proving this from the fact that k is closed. And the computer just knew that because x is compact, k times x is compact. Okay, so let's move to the key part of the argument. If there is no question about the general way you use this thing, is it clear whether this dialogue we have between the user and the computer answering on the right-hand side of the screen and helping a bit with the boring parts of the proof? No questions about this? Now, I will, what? I lost my, I prepared, so there was something weird with the program being left, sorry, I need to type more than I wanted to type. So I want to obtain P, I want to obtain the following statement. So there exists P or maybe, no, I will cheat, sorry. I prepared this, but then the computer did something bad. So I will just copy paste this from the solution file because it's too long to type otherwise. So I want to get this P using the extreme value theorem. And so again, if you want to know what is this extreme value theorem, you can ask for suggestion, you can ask the computer to suggest something. And there is something suggested, which is, what is it for? That one is using the compactness assumption. And now I've got three goals. And there is some problem here. And the computer is asking why K is not empty. You see that? So the next goal is proving K is non-empty. So why K is non-empty? Let's go back to my proof. Oh, there is no mention of K being non-empty in this proof. So what happened? Why is it non-empty? Well, there's no reason it would be non-empty. I mean, for instance, if F is constant, then clearly K is empty. So this proof is, I mean, it's a nice proof to prove uniform continuity of continuous function, but it fails for constant function, which is, okay, maybe a bit disappointed, but okay, I've got my solution file where I know that actually I could have done something more clever, which is, okay, maybe I will stay on this solution file now. I do a case disjunction depending on whether K is empty or not. So I'm using this command cases, so I discuss depending whether K is empty or non-empty. And in the case K is empty, I've got to do something. And actually, I need to type 4 lines that I wanted to skip anyway to handle the case where K is empty. And then I'm back on track. And when I'm back on track, I can indeed apply the extreme value theorem and get my delta, my P that I wanted. And then the next step of the proof was, let's use delta is the distance between P1 and P2. So I just copy the same thing to the computer. And again, I'm disappointed because the goal is not the goal I expected. The new goal is made of 2 parts. So this funny symbol is the logician way of writing and. So this is a conjunction symbol. I'm asking for the proof, that my delta is positive. So where was that proof in my slide? What did you tell me to prove delta is positive? And now what I tell my student in this situation is, look, you start the first line of the proof is fix epsilon a positive real number. And then where do I use the fact that epsilon is positive? Nowhere. So that's a pretty bad omen. So probably now is the time to use that epsilon is positive, and that will prove that delta is positive. So, and indeed there is a small proof to do. And after doing that, I know that the delta is positive, and I have to prove the goal that I announced. And then this is the contraposition that I announced, and there is no more gap in the proof. Okay, so this is what it looks like to prove something, to explain something to a computer, and at the end the computer is convinced and it writes all accomplished, and you're done. You've checked the encounter skill. Are there questions about that part of the talk? So of course you're not meant to now be able to use the software and be an expert in that. Just give the flavor of what it looks like to explain mathematics to a computer.
So when the computer suggests you could try this and that,
yeah.
does it mean that the computer knows in advance that any of these ways will lead?
No, it will lead to some progress, but sometimes it's a bit stupid, the suggestion that the computer gives.
No, but this is very long. I mean, does he suggest a very long way to prove it, or is it that he doesn't know at the beginning with the suggests whether this is anywhere?
No, I mean, that suggestion command is pretty dumb. It just tries to apply all lemmas that are currently in scope that has been explained. And if any lemma makes any progress, it suggests applying it.
Not progress.
Like something, not failing to apply.
I think it could lead you on a path that cannot be proven.
Oh yeah, I mean progress in a very local sense. I mean, if it managed to apply a lemma,
But these are all lemmas that can be applied to.
But there is no guarantee that.
There is no guarantee that. So, for instance, if we return to this, maybe it's clear if I go back here.
There is one question also for you later. Someone is asking what's the difference between have and obtain?
Oh, it's I mean, it's a technical difference. But I want to. You see, when we write on paper, we are very, very sloppy with existential statements. When we write on paper, there exists delta such that, then the reader almost always is meant to understand that you fixed some delta such that this is true. And but from a logical point of view, there are two steps: just asserting the existence of delta and fixing one delta. And the obtain command is doing both at the same time. This is already a small shortcut to do that at the same time. So let me see, let me show close that sometimes the suggestions are a bit stupid. So for instance, you see, when I wanted to prove that K is closed, the computer suggests that I could refine that, I could use that, I could prove the complement is open. But it also, which is not too stupid, but then the next suggestion is to apply the fact that a finite set is closed in a T0 space. And then if I follow this suggestion, then the computer will happily ask me to prove that K is finite, which is of course a complete dead end. So the computer is not yet proving everything for us. I mean, there are people who dream of having computers solving difficult proof problems, but we are not there yet. Now, something that we could have done in the beginning was to ask suggestion in the very beginning of the proof. So I just remove all this and ask for suggestion. And then the computer has a very nice suggestion, which is to apply the encounter theorem. This is good. I mean, this works. And we can have a look at what is the proof of the encounter theorem. Just hit the button and just jump to the proof. And you'll see that this is the proof of encounter that the computer already knows about. This is this computation. So maybe it's a bit hard to read, but I think I've got a version, a text version of this somewhere. Yeah, I should. Yeah, this is the text version of the proof of the computer of encounter. And maybe it doesn't look like. Sorry, the message. I don't really need to see that all the time. So this is the proof that is in the library of mathematics that the computer already knows about. And maybe the first surprise that it doesn't start with let x and y be metric spaces, it starts with uniform spaces, because this is not a L1 course, so we are doing general stuff. And then there is this computation, and this computation is about some abstract stuff that are called filters. And it's a very convenient way of doing analysis on paper or in computers. But on papers, we don't use that. So this is technology invented by Bobecki in the 40s, but that we don't use on paper, and we don't teach that to our students. But when you want to explain mathematics to a computer, you really need the efficient abstraction and the most beautiful theory that you can get. And this is why we use this everywhere in proof. But I don't have too much time for propaganda for filters, because I also need to, I could lecture all day long about filters and modern view. This is modernized Bourbaki. It's not as nice in Bourbaki. Bourbaki is a bit too concrete and not enough tutorial, but we fixed that. Now we have a very nice story to tell. And then Bourbaki is a bit shy with filters. They use filters a bit, but we use filters everywhere. Yeah.
So all these proofs that are being suggested to you, do they belong to some standard libraries?
Yeah, so they are all in a standard library that we are writing. When I say we, it's 200 people have contributed so far, and this is all public. And you can so all on GitHub, and you can contribute. You can start contributing tomorrow, and that's fine. We'll be very happy. Okay, so I still want to very quickly explain what this is good for. So the first thing, which is, of course, we are still academics and researchers, so the actual motivation is we are having fun doing that, and it's nice, and but still we need to rationalize and motivate with other things. So the first obvious motivation is checking proofs. So of course, the proof of encounters that I explained is not so nice in the end. It was full of gaps, and I found this proof on Wikipedia. And at first, I thought it was a nice proof, and then when I realized all the small gaps in it, I was not so happy with this proof anymore. So Johan already explained yesterday in his colloquium talk that what is currently possible with current day technology is to check very carefully chosen technical fragments of a larger project. It's not reasonable that we start checking all of research level mathematics now, and the computer is not smart enough, and there are not enough people doing that, so they couldn't be feasible in a reasonable time. But if you have something very specific to check, very technical, and the prerequisites are there or mostly already explained to computer, then you can do that and get superhuman certainty that something is correct. So this is what Scholze asked us to do 1.5 years ago, and so we can already do that. This is not the main motivation for me. For me, the main motivation is explaining mathematics. So in explaining mathematics, what I mean is that in traditional math writing, the author decides on the level of details. So maybe when I wrote that slide about encounter, I decided that, okay, maybe K being non-empty was a natural slip, but maybe the fact that delta is positive, I didn't want to explain because I think that my readers are smart people. And if you are the reader and you don't know why delta is positive, you're completely stuck. And when you are the writer, you cannot always explain all the details everywhere, because if you do that, you just end up with a document that nobody can read. It's completely unreadable for everybody. So the goal is to have, the dream is to have interactive documents where the reader decides on the level of details. You start with a couple of drawings and maybe a video and a proof sketch, and then if the reader wants to have more detail about one statement here, just click here, I want a detailed statement, and then then it can click, or she can click, I want to see a proof sketch, and then I want to see detail about that step in the proof, and then maybe you ask for too much detail and you regret because it's really awful, so you back up and just go to a higher overview. And this doesn't currently exist, but it should be doable in the near future. And yeah, this is for me. This is really the main thing. So if you remember only one thing from this explanation is we want to explain mathematics to computers because we want human readers to be able to choose the level of details when reading mathematics. This is really, for me, the main point. But then I also use this for teaching, because it's teaching how to prove stuff, so teaching proof to students. And yeah, I don't have really time to show you, but I mean, I'm using this in our site to teach first-year undergrad. So they are elite first year, and they are selected students in a double major track, but still they are actual first-year students. And the way I'm using this is the goal is to write good proofs on paper that anyone can read, even people who have never seen a computer in their life. But I use the computer as an intermediate step, and the main point for me is this dialogue between the prover and the computer, where you see at each step of the proof what you have to prove and what are the assumptions. This is not, the main point is not that the computer is really serious and cannot be cheated. The main point is that the computer is always explaining what are the current assumptions and what is the current goal. And it's not so easy to translate such proofs that you've seen on the screen on paper. So because of that, I've added a bit of a layer of interface where students can read proofs that looks more like paper proof. So this is the same software, but with a small extra layer of custom comments. And you can see, so this is proving that if f is continuous at x0, then it is sequentially continuous at f0, at x0. And you see the proof reads more like a French language proof. Montrons que un soit, etc. Montrons que n convient. And then when they write this, then it's easier to go to a paper proof after writing such a controlled natural language. So I've been using this for 4 years in our site. And then the last motivation part is I think that this computer technology could help to create mathematics. And in our research work, and there are several ways it can help. I mean, it's easy to tweak things when they are formalized. You can change the definition a bit, see what breaks, see what proofs still work, and you can change slightly the statement of the lemma without fearing that maybe there is one use of this lemma you forgot about, and the new shape of the lemma is not good for that specific use and stuff like that. It's very fun to find unnecessary assumptions in proof using the computer. First, you can ask the computer, did I use all the assumptions? And for instance, it happened to me while explaining completions of topological rings to the computer, and in Bourbaki general topologies, there is an assumption that is completely useless in one of the theorem. I don't know, it's a typo in the statement. And in the beginning, I put all the assumptions, I explained the proof to the computer. At the end of the proof, I think I've never used this, but because this assumption was a completeness assumption, I thought maybe it was used automatically in invoking some lemma, but I removed the completeness assumption. The computer was still happy. It was very nice to remove an assumption like this. Okay, but this is a bit tiny helps. But the more serious goal is that searching for mathematics should become much easier. And we hope that with the help of a bit of artificial intelligence, we'll be able to ask the computer not only suggest something for me, but is there any lemma that has been formalized, that has been explained to a computer that vaguely looks like what I'm trying to prove? And the vaguely looks like, this is the kind of things that neural networks are good at. And so hopefully we get a very powerful search for mathematical statement and definition, but currently this is science fiction.
In your own library, or you would say like on paper mathematics?
No, on paper it doesn't work because
anyone ever publish a lemma that would prove this, and then he would tell you in the
no,
1960.
that would be even more science fiction. Of course, there are people who claim that they will just download all archive and then use artificial intelligence to turn the archive paper to proofs like this, and we know, at least in our field, that won't work. But there are people who are very optimistic. I know those guys working in artificial intelligence, they are very optimistic. But again, it's easy to look, but 10 years ago, people playing Go felt completely safe before the computer would never be able to play Go correctly, and that the people playing chess were so stupid to play a game that computers could play, and now they are not laughing anymore. So you should be careful. But, anyway, but artificial intelligence may help also filling easy proofs or suggesting analogies, maybe. And I've shown you a bit already that the formalization encourages clean abstractions. You really need to think clearly and get the right definitions, and this is what I've shown you with filters. I don't have too much time to explain filters because I've got the second half of my talk to give, and I'm already 5 minutes over time for the first half. So if you don't have more questions, I will talk about differential topology and the project I'm currently working on. Okay? So when people see that kind of software, they usually think that this is good enough for combinatorics and algebra and stuff like that. Although what I've shown is more a bit of analysis, but extremely elementary analysis. But for a long time, because the only people who were using such software were computer scientists, they were checking things about graphs and finite groups, and they did wonders with such simple objects. But it was not clear that you could do any kind of mathematics, explain any kind of mathematics to a computer. And so in response to that, a couple of years ago with Johan Comlin, who is here, and Kevin Buzzard, we decided to explain modern mathematics and sophisticated definitions of a computer. So we explained the definition of perfectoid spaces, which is a gadget in arithmetic geometry that was and is still extremely fashionable, because it was a gadget invented by Peter Scholze for the purpose of getting the Field Medal, and probably doing something in arithmetic geometry. I've never understood what exactly, but so we explained that definition to a computer. But this was still very algebraic. And the perfectoid spaces, you need a mix of commutative algebra, general topology, and algebraic geometry. But this is still not the kind of mathematics where you scribble a little drawing on the blackboard and this is meant to be a proof. So the next challenge was to be able to explain a bit of differential topology, which is, by the way, the kind of mathematics I'm doing when I'm actually working instead of playing video games. So I wanted to explain differential topology, and the most famous piece of differential topology that is very visual and that people know about is the sphere eversion trick. So if you don't know about this, we can just very quickly review. So this is part of the outside-in view. It's really lame. So you've got a surface and you're allowed to deform it, you're allowed to make it go through itself, but you are not allowed to tear it, or you are not allowed to crease the surface. So if you just make a sharp crease, then the surface explodes. And the goal is to take a sphere in 3 space, S2 in 3 sphere, and turn it inside out. So the one side is golden in this video, and the other side is purple, I think. And you try to follow these rules and turn the sphere inside out. So if you do it naively, you get a huge crease along the equator. So this is forbidden. And then there is in the video they try various stupid things to do. And then there is a very complicated way of doing it. We'll see it in a moment. But the question was, can we explain that to a computer? Because, again, for communication purposes, we wanted to choose a project that everybody, many people have already seen such videos and know this is really differential topology. And notice is a complicated way to do it that Thurston found at that time. And here you can see it works. And then there are many more videos of different ways of doing this, and so I decided it would be a nice project to explain this kind of mathematics to a computer. So this is another way to do it. So we started doing that actually 2 years ago, but we got interrupted by the helping Scholze with his condensed mathematics stuff, and we really started seriously last September, and we are, on paper, I would say we are almost done. We have done all the core proof, explained the core of the proof to the computer. So what we've been doing is not explaining one of those videos to the computer. What we are doing is explaining a general theorem that completely crushes the existence of this eversion. So in technical terms, we've been proving flexibility of open and ample partial differential relations. So I won't define all this. I will just explain in the case of sphere eversion. But what we are doing is really a general theory, general differential topology that proves existence of sphere eversion as a very easy corollary. So how does it work? So I will now switch on the blackboard because I need to explain the mathematical content of this story. No. Because this afternoon, Floris will explain more details about the part of the proof that is the most complicated to explain to a computer, but in order to motivate this part, I need to explain the context. Yes, there was a question.
No.
So the question is how to turn a sphere inside out. So I want to do this in essentially 2 easy steps. So first, this is a completely local story. If I understand how to, so the technical word is immerse a piece of plane inside space, then I can do this locally. My sphere locally looks like a piece of plane, and everything is local in this story. And what we fully formalize is exactly the local part of the story, but we haven't fully formalized the piecing things together to get the statements about manifolds. But you have to believe me that the key thing is to turn any map F from a plane to space into a map whose derivative is injective. So the technical thing about not having creases or pinched point is adding an injective derivative. So into some F bar, which is C0 close to F. So as close as I want to F in a C0 topology, but has injective derivative. So the total derivative of F is injective at all points. So this is what this condition of injectivity ensures that the image of F in R3 looks like a smooth surface. It's a honest smooth surface without trees or sharp edges. Okay, and there are 2 easy steps. The first step is to make sure that the derivative, say in the x direction, maybe I would call xy the points in R2. First step, so make sure that the partial derivative in the x direction of x at xy is non-zero. And the second step, we need to make sure not only the partial derivative in the y direction is non-zero, but it's also not in the span of the first one. It's not a line spanned by the first derivative. You see, I want to improve the partial derivatives of f. I want to improve f one partial derivative at a time. And the first partial derivative, I just want it to be non-vanishing. And the second partial derivative, I want it to be not in the line spanned by the first one. So that would be making some intermediate function. So that would be giving some function f1. And then, I mean, I call all the functions f, but you need to understand I start with some f, and then I modify it to get a new function that I still call f, which satisfies this first partial derivative condition. And then that second function is modified to a third function. There was a question, Klaus?
That was the question. F is.
Yeah, f is not, I mean, f is changing from line to line. Okay? And now, how can you do that in a kind of, again, a principled way? I don't want a specific proof only for sphere eversions. I really want to get a big machine that also proves other kind of theorem. And the big machine, you've probably heard of it if you're in Lyon, because it's a machine of convex integration that Vincent likes very much. So how does it work, this convex integration machine? Convex integration. So I need to explain why convexity enters the picture, and I need to explain how integration helps. So there is a toy model to understand how convexity can enter this picture. It's because I want to get a solution that is very close to my initial map. So there is a toy case. And I will assume the source is one-dimensional. So assume I have that f is a function on real numbers with value in some vector space. And it is smooth, so a C-infinity function. Assume I've got a subset omega in E, and a sequence of function Fn such that two conditions are satisfied. So Fn converges C0 to F, so uniformly on compact set or something like this. So it doesn't matter for the level of detail I'm using. And for all t in R, for all n, the derivative of Fn of t is in omega. So maybe in our first situation, omega would be simply R3 minus 0. And I'm interested in function with non-vanishing derivative. And I mean, in the second case, the setup would be a bit more complicated because omega would depend on t, but I'm just focusing on the simplest situation where the source is one-dimensional, and you've got a derivative problem. You're interested in function whose derivatives takes values in some omega that you fix. And you want to understand what it implies for a function f that it is a C0 limit of a function whose derivative takes value in omega. Is that clear of the problem I'm looking at? So the question is, what can I say about f, knowing that f is a C0 limit of a sequence of functions whose derivatives takes value in omega? And then the claim is that for all t, the derivative of f is in the closure of the convex hull of omega. This is the claim. And this is how, so conv is the convex hull here. And this is how geometry enters the picture, which is very surprising because this is all about differential topology. So there are derivatives, so this is differential, but there is no geometry at all a priori. And this toy lemma says that the geometry of omega, you can see something of the geometry of omega. And in particular, if you don't know whether such a sequence exists, then you get a geometric constraint on omega that is necessary condition for the existence of this sequence. Is it clear what is the statement here? And the proof of this is very easy. This is a nice exercise. Maybe I will prove that, because otherwise it's kind of magical. And yeah, let's do that. So without loss of generality, I can assume, after maybe extracting a subsequence, that the C0 distance between f and fn is a big O of 1 over n squared. And then I'm computing this. I want to compute f dot of t. I'm considering for any positive n, f of t plus 1 over n minus f of t divided by 1 over n. So this will tend to f dot of t when n goes to infinity. And I can just insert my fn function everywhere. The board is not light enough. Yeah, maybe I should do this computation on a whiteboard board. This is I was writing, so f n minus fn of t plus 1 over n divided by 1 over n. Then there is a term that I just introduced and that I'm removing. And I'm comparing with this. That's this fn of t minus f of t divided by 1 over n. So since I don't have a computer checking my computations, I need you. Did I mess up this? So I introduced fn of t plus 1 over n and fn of t, and I should have removed everything that I introduced. I think it's okay. Okay, so that first one is, so this is big O of 1 over n, and then I multiply by n, so this is big O of 1 over n, and the same here. And this is the integral from 0 to 1 of fn dot plus s divided by n ds. I'm just using the fundamental theorem of calculus and, to write this. And now this belongs to the convex hull of omega, because all this is in omega. And so if you look at the Riemann sum approximation of this integral, this will be in the convex hull of omega, and then the integral belongs to the closure of the convex hull of omega. And the left-hand side was converging to f dot of t. Okay? And so it's very elementary computation, but it shows that if you want to understand what are the necessary conditions if you want to approximate in a C0 sense any function by a sequence or a family of functions whose derivative has to take value in some prescribed set, then the convex hull of this prescribed set will show up. And now there is a converse to this. There is a converse to this result. Essentially, the converse is almost true. If you have a function and the derivative is everywhere in the interior of this convex hull instead of being in the closure of this convex hull, then you can build a sequence of approximation. And here is an idea of how to prove the converse, or a kind of converse. So let's say you've got your function f, but this is the image of f, and maybe the target is a plane. And say at t equals 0, you've got the speed vector f dot of 0. And somewhere in this vector space, there is a set omega, like this. And you know that this vector, this derivative, is in the convex hull of omega. So by assumption, there are some, what it means that it's in the convex hull, you can take here in this case 3 points. And this vector f dot of 0 is a barycentric combination of those 3 vectors. So maybe I need more color. I don't have color. I was meant to give a computer talk. I'm punished for returning to my old bad habits of drawing little pictures instead of being rigorous. Yeah. So let's try this. So we know this is maybe a combination of this vector and this vector and this vector. So what I can do if let's say it's 1/2 this vector plus 1/4 of the other vectors, I can follow the direction. So I know I want to construct my f bar map, my approximation of this map f whose derivative is everywhere in omega. Then I follow for some time proportional to the barycentric coefficient this direction, and then I need to follow the blue direction for some time, and then I need to follow the green direction for some time, but the amount of time is given by the barycentric coefficients, and I do that during a time epsilon, and then I get a new trajectory which is piecewise affine. And which will be very close at the end of the trajectory. I will be very close to f of epsilon. But you see that the issue with this drawing is that I'm not building a smooth function f because I've got corners everywhere. So this is pretty bad. I need to smooth corners. So, but if I smooth corner and I still want my derivatives to be in omega for all time, I better make sure that these points can be linked in omega. and they are in the same connected component of omega. So you see that somehow I will need to interpolate between these 3 points. So maybe the derivative path that I will follow in order to smooth corner will look like this. And also, I know I want to start again between epsilon and 2 epsilon to get an approximation of the next piece of the curve. Then I need to make sure that I go back to my starting point in terms of derivatives. So because of this, you see that you will need to build loops. And this is a pretty fuzzy argument. But again, I don't want to get rid of fuzzy arguments. I want to get the whole spectrum of fuzzy pictures all the way to axioms of mathematics with hopefully smooth transition, which is not yet the case. But the computer dream is this, that we can have documents with I don't know, homoflight pictures and all the way down to axioms of mathematics. So this sketch was meant to convince you that what you really want is something like this. You want a family of loops. So from your starting point, so if you want to improve a map which is defined on a vector space E with value in a vector space F, you need a family, and you want to improve in the derivative. Improve the derivative of F, which goes from E capital F in direction V, some vector V. You need a family of loops which is parameterized by E with value in F. So set that for all X, the map gamma X, so which is a gamma of X, comma dot going from S1 to F, takes value in a nice set. That would be in the omega set. And has average value. The average value is just the integral over S1 of gamma X is the derivative of my original map in the direction V. And at least if E is one-dimensional, so this is the story that
What's V in your
V, so in a case where the source is one-dimensional, V is simply d over dt. But if I've got more derivatives to fix, like in my first example of sphere eversion, then the V would be first d over dx and then d over dy.
because it does not show up on the left in your notation.
On the left.
Then you have something called gamma X bar, which does not mention any V. And on
Yes.
the right you have a V.
Yeah, that's fine.
Okay, fine.
I want so
V,
gamma will
V
depend on
is
V.
given.
Yeah.
V is given forever.
So in the first step, when I had 2 steps in the beginning, the first step I was modifying the F in the direction of X. So the V would be the first basis vector, and then I'm doing my stuff with some family of loops, and then the second step V would be a second basis vector. And you see here gamma would be this. The image of gamma would be this thing in my picture, because it has to be related to some kind of average value condition like I had before, but it's not enough to have only 3 vectors, because if I use only 3 vectors, I will have a piecewise smooth path. So I need a full path of vectors in omega, and it needs to be a loop, because I want to come back where I started, because then I want to continue building my approximation. So it looks like the final proof will be extremely messy, even if I have this ingredient that for each point in my source, I have this family of loops whose average value is the derivative of my map in this direction, and it takes value in the relevant set. So in the relevant step, in step 1 of my sphere eversion, idea was simply all non-zero vectors, and in step 2 it was the complement of a line of the subspace spanned by the first derivative. But fortunately, there is a very nice implementation of this idea, which began here in Lyon in the PhD thesis of Mélanie Théière. And so all the picture and all these nice ideas that I've described so far are due to Gromov. But then in Gromov's explanation of the story, there is a lot of room for interpretation, and details are very much left to the reader. And several people implemented those details in various ways, but the modern way of doing that was created here in Lyon. So I will finish, if I can go over time, 3 minutes, with Mélanie Théière implementation. So once you have this, this family of loops, so we are in this setup. For any linear map whose kernel is supplementary to V, so for any phi, so a linear map from E to R, so that I will even say phi of V equals 1. So so pi is a linear form, and the kernel of pi is made of direction where I don't want to change the derivative of my map because I'm already happy with the derivative in this direction, and I only want to change the derivative in the direction of V. I simply set for some positive number n, we can set f bar of x, f of x plus 1 over n integral from 0 to n times phi of x, gamma x of t minus gamma x bar. So this formula, I claim that if you use your family of loops gamma sub x, so again x is a point in the source space E, and gamma sub x is simply I fix the first input here to be x, then you can write a very simple formula involving this integral, and the claim that I won't have time to prove because I'm short on time, but this is really a 5 minutes long proof, not more complicated than the proofs I'm just erasing, or it's a bit more complicated than the proof I'm just erasing. The claim is that, so first, for n big enough, this f bar is C0 close to f. So you modify, so that one is obvious, everything is periodic in the integral, and the whole integral is divided by n. So you get something which is very C0 close to n. And if you look at the differential of this f bar in the direction of V, is almost a value of gamma x. So if you were happy with the place where gamma x was taking value, then the new derivative is a good one. And for all w in the kernel of phi, which are meant to be the directions you don't want to touch too much, the derivative of f bar at x evaluated in w is almost what you started with. So you are not destroying the work you've been doing on the other directions when you do that multiple times. And this lemma, which again is Théière's lemma, is very easy to prove on paper, and it's also very easy to explain on a computer. I know I'm not writing more proofs because Floris in the afternoon will explain how you can build such families of loops. So he will explain how to solve this problem where you've got like this two vector spaces E and F, and you want to build loops whose values are constrained to be in a certain set, and you want the average value to be a given function, here df of x applied to V. And actually, this part of the problem is much more complicated. If you write the full proof, that part is much longer than running the convex integration itself. I mean, this thing about differentiating integrals and controlling stuff, proving that two functions are almost equal and the derivative in certain directions are almost equal, this is all pretty easy to explain to computers. But in this setup where you want to build loops, there are a lot more little drawings in the proof and a lot of things that are typical in topology, where you explain how to do things locally, but then you want to glue stuff that you've done locally, and so you need to get a way to change your mind. And if you've got you do things locally on one open set and locally on another open set, so on the overlap you have two solutions, and so you need what I call a satisfied or refound lemma, saying that you can change your mind continuously on the overlap and extend stuff. And all this is a lot more technical to explain to computers than calculus, but it still works. So this has been completely explained to the computer. The local theory, how to build loops, has been explained, and how to do convex integration using this formula and slightly more sophisticated versions that are needed when you want to cut off things near the boundary of an open set or something like this. This has all been explained. What is not completely done yet is having a statement which is all about differentiable manifolds. If you want to explain that we can do it in charts and using vector bundles and stuff like that, this is not yet fully explained. On paper, that part is one line long. I mean, that part on paper is saying that what we've done locally is obviously enough to get the global state. And I don't think there is anything more you can write on paper. Because the way it solves differential geometry or differential topology construction problems, this method is so well controlled that there is no problem implementing it everywhere. Because if you start working in one chart of a manifold, okay, you can do whatever you want in that chart, and because you're not modifying stuff in a C0 topology much, you won't spill over the next chart or anything like this, so you do it in the first chart. And then in the second chart, you want to continue building your solution in the second chart, but without ruining what you've already done in the first chart. But because all this works relative to any place where you're already happy, I mean, if you're already happy with the derivative of f on some closed subset, then you can do this construction without touching this closed subset where you're already happy. And so everything is very easy to globalize, but of course the computer doesn't like this is obviously easy to globalize argument. We'll see whether we can convince the computer. But at least we know that the calculus, I mean, stuff with general topology coverings and refining covering, and just having cutoff function and stuff, this already works great. And having calculus unintegration already works great. And we have very general versions. For instance, here we need to differentiate this function, which is a parametric integral. So of course, in this situation, we are integrating a smooth function, a C-infinity function on a segment. So this is extremely easy to differentiate under the integral sign. But because we are building this big library, which is meant to be usable for many purposes, we proved absurdly general statements about I don't know what, functions taking values in Banach spaces with a local Lipschitz bound of the derivative at this point, and maybe on an ego or something. And this is a good transition to Sebastian's talk. We'll explain absurdly general version of the change of variable formula. So, but yeah, that's all.
Other questions? Either on the first or on the second part.
So there is one question online. I don't know. What did we do with the speaker?
What?
I don't remember if we did something with the speaker, with the.
Oh, you mean we should be able to? No, but I didn't do anything here.
it was muted at the beginning on the keyboard. Unmute the sound.
No, but the sound on my computer, but not on this.
No, it was
Not on this computer. I don't know.
Otherwise, maybe people can write down questions and we
Yeah,
can read them aloud.
People was already answering questions. But I think nobody is trying to talk.
No, maybe no. Okay, no. There's no question.
Yeah, I'm sorry, the second part was a bit fast, but I had 2 talks to give in 1 hour.
Thank you very much.
Yeah, I have a question more about the first part.
Yeah.
So what's the starting point of the mathematical formalization?
You
How
mean
do
the
you
axioms?
implement the action? And then...
Yeah, we don't care about that. We are doing mathematics. So I mean, there are people who thought very hard about these questions. I mean, very clever people, and they told us those are the axioms. But when we actually do mathematics, you've seen me explaining mathematics to a computer, and it was completely irrelevant what were the axioms, like in real life. I mean, we have this polite lie when we do mathematics, and sometimes we tell the philosophers who are curious about it that we are based on what Zermelo-Frankel something, but nobody is able to list any of the axioms of Zermelo-Frankel. Maybe in this department there are people doing logic who can, but at least this is how I do mathematics usually, and I have no idea what are the axioms of set theory, and I don't have much idea about what are the axioms of type theory that are actually used by the software. So the problem with set theory is that everything is a set. There is a completely amorphous theory, and everything is a set, and there is only one relation. There is equality, and there is a membership in the set, and everything is encoded in this stuff. And this is very bad for computers to help us because when you type garbage in type theory, so for instance, maybe a garbage question is it true that pi, the circle constant, belongs to cosine? And this is a perfectly well-formed question in the Zermelo-Frankel set theory because pi is a set because they are only set. Cosine is also a set because everything is a set. And membership is well defined for any set. That can be a member of any set. And now, when you accidentally type such garbage on your computer, if the computer is really believing in set theory, there will be no complaint. There will be a perfectly fine statement, and then it cannot help you. So what we use instead is something called type theory, where every mathematical object has some type, and there is a type of real numbers and a type of function from real numbers to real number, and this question doesn't make sense in type theory. So there are a lot less garbage results that you can state in type theory. You can still, with some effort, you can still state some garbage question anyway, but for the computer, it's much easier to help us in this situation. And yeah, I don't have the screen again, but the computer really keeps track of what is everything. So for instance, in my proof, I had stuff like distance between P1 and P2 is less than, maybe sometimes there were distance between P1 and P2, and on the next line there will be distance between f of P1 and f of P2. But if I still had the screen down, I could ask the computer, what is D in that case? And the computer would say, this is a distance function on Y. And that one is a distance function on X, because it carefully keeps track of what is the type of each object. And it says, okay, P1 has type X, and P2 has type X. So this distance function will be a function on X times X. So it must be the distance function on X. Whereas in set theory, you just tell me, oh, this is a set, this is a set, this is a set, this is a set, this is also a set, and P1 is a set, F is a set, and P2 is a set. And that's why we don't use this foundation. But now the specific details of the flavor of type theory that we are using and the specific axioms, I'm completely incompetent to answer that question. There is one thing I can say is that a lot of people on the computer science side of proof assistance are are very interested in constructive mathematics. They want every existent statement to be backed by an algorithm computing something, and this has profound implication on the way they explain mathematics to computer. It makes a lot of things much more complicated, and everything I've shown you today has been done by people who don't care at all about these questions, and because we are doing something else. So we have no problem using excluding middle law, no problem using axiom of choice if it helps, and the computer doesn't complain about all this at all. It just registers that we are using those axioms, but it doesn't care. Yeah.
I mean, maybe there's one precise statement that can be made that you can prove a theorem saying that the foundations that we use are logically equivalent. Like,
Yeah, you can. Yeah, you can embed the foundation that we use inside ZFC if you have sufficiently many big sets, like inaccessible cardinals. And conversely, you can embed ZFC in the axiom that we use. Yeah, so there are equivalencies. At least if you believe in the existence of big sets.
that's the axiom of infinity, right? That's the axiom of infinity.
No. The axiom of infinity is about.
You claim you didn't know the axioms.
I mean, I couldn't write the axiom of infinity, but I know that it gives you one infinite set. But if you want to embed the type theory, you need much bigger sets. And I don't really know what much bigger means. But people really.
We're already a little bit late, so if you have more questions, maybe we will ask them during lunch. Let's